So hello folks, and again you're all very welcome back to episode 5 of the Formula 1 technical video series. Now I'll admit the production of videos took a bit of a slump over the last year, mainly because they just weren't getting any viewership at all. You know, I guess it's a very niche avenue on YouTube, but the good news is in the last 2.5 weeks, the views have spiked enormously. You know, they were sitting at about, I think, 2,000 views on all the videos, on the first video, and it's spiked up to about 22,000 views just last week. So obviously, the 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 algorithm in YouTube has changed, or it's been linked on a forum or something like that. But the views have been off the charts, as well as the subscribers. I think it was sitting at about 213 for about the last year, and it's nearly at 1,000 now. So it's just spurred me on a good bit to do another video, you know. So I guess really it's up to the viewers on the channel. As cliche that is, and you'd hear people saying it on YouTube, you know, that, oh, like and subscribe and all that. I'm not really into that, or I'm not going to say that, but it's obviously sharing the videos that gets the views, which further on, you know, gives me the motivation to make more videos, because people are watching them and they're learning and they're commenting. So just to get that bit of chat out of the way first, I also added a buy me a coffee link, because these parts, you know, it's not like buying something, you know, for 10 or 20 euros in Poundland and doing a tear down, or, you know, getting sent, I don't know, a new drill of whatever manufacturer. Like these parts, they're extremely hard to find, first of all. Normally you just can't buy them if you're, you know, a normal person. It's kind of a closed circle of people that know where they are and who deals in them. Secondly, knowing what the parts actually are, which can be a hard one. And thirdly, just the cost of them. You know, these are not, in the words of the film Gone in 60 Seconds, these are not Honda Civics. They're most of the time they're extremely expensive parts to purchase. You know, even if they are, you know, scrap or can never be used again. So there's a link in the top. I hate saying this. There's a link in the top, up there. It's beside my. It's up on the top main image, the oblong shaped image. It's to the right hand side of my LinkedIn profile. You can click that and it'll bring you into the Buy Me Coffee site. You can just, whatever, submit €5. And also there's a commissions section of that site where there's other things on offer, including actually this part and many others for sale if you want to buy it. So with that, we'll dive into the part. So I'll just check how my video is and check the time and see are we all right. It's been a while. Yeah, we're doing good. All right, so I bought this part about what, I'd say probably 3 months ago, off a guy in the UK, a seller in the UK. Now I have done an article on F1 Technical on the part. Now the guy selling it didn't know what it was. Now I didn't know what it was either by looking at it, but it became apparent when I started tearing down exactly what it was. It's about 250mm long. It's off the Williams Bmw FW25. What year that was, I can't remember. 2003 or 2005, I don't know. But after a bit of a tear down, it became apparent that it's a piston displacer, a piston accumulator and an oil water cooler, or, you know, heat exchanger. So I've covered already in a previous video of the hydraulic oil pump teardown video. That had got a diaphragm accumulator on it, one of the Honda parts, which is basically as described. You know, it's a tank with a diaphragm in the middle of it. On one side there's hydraulic oil, on the other side there's nitrogen gas, and that's pressurized so that the oil can, you know, get bigger as it increases in temperature, or if there's pulsations from the pump, it smooths those pulsations, those sinusoidal ripples, or it also It just allows the oil to take up a further space if you've got like a two-way, a two-way ram actuator from Moog or something like that. Whereas whereby the volume underneath a double action ram, the volume underneath the piston is greater than the volume on top of the piston, because you've got the piston shaft coming out on top of the piston plunger itself, so the volume of oil is less there than it is on the bottom. The same with an automotive damper, why you'd have to have the outer cavity also pressurized with gas, because the displacement is different above and below the piston rod. So that's basically it. I mean, there's a few key differences between a piston type accumulator and a diaphragm type. Generally, the piston type accumulator is more robust. Granted, it's heavier, but it can flow a lot more generally. It tends to fail a lot slower as well. Whereas if a diaphragm type accumulator fails, it'll just be gone like that, in a second. Whereas this will fail slowly, because it's like a single action ram with nitrogen behind it and the oil in front of it. So it tends to fail a lot slower. Now, in terms of response rate, the diaphragm type accumulator will have a better response rate because the inertia of the diaphragm is so low, whereas this is quite a big, it's a big piston, it's a shaft on it, so it takes longer to react. As well as that, if let's say you had, I don't know, 1,000 psi of nitrogen gas behind it, in terms of pressure accumulation, it could take 1,010 psi to move it because of stiction with the seal in the bore. So not as fast to react, but more reliable, and it can flow more because just of its nature, and generally they can take higher pressure as well. Like if you put ginormous pressure behind a nitrogen or behind a rubber diaphragm accumulator, it would actually just destroy the diaphragm, because it would literally squeeze it in, like it was in a huge vacuum. It'd squeeze it into ports and different places, and it'd just rupture it. Whereas this could take a fair amount of abuse. So I'll probably break this video into two parts, just keep the video short enough for my end for uploading. But I will talk you through roughly how it is in terms of overview first, and then start tearing it down. Now, the whole assembly itself is in two parts. It's got a kind of a very cool manufacturing feature in here, in the oil to water heat exchanger, which I'll show you in a moment. But it's got various takeoffs and drillings and all that, which I'm not really going to go through. All these ports, takeoff ports, fill ports, water ports, and again as well we have got a linear transducer here, which it basically captures the position of the piston, where it is in the bore. So the ECU will know. The ECU can look at all the parameters of various sensors, what are open, closed, what oil volume should be where, how much is in here. I mean, it knows the oil volume as well in the hard coding. And if there's anything amiss here in terms of piston position, it'll know that, hang on a second, there's something wrong, and it'll flag a fault, with the position of the piston inside. So let's take off a few parts and have a look what's going inside. Now, in terms of materials, this is hard anodized, as you can see, with a brownish color. Hard anodized aluminium alloy, probably a 7 series or a 2 series. These again would be aluminium. Any of the real shiny silvery parts would be titanium. There's a titanium clasp here which holds in a bung. Titanium again, titanium. This would be carbon fiber. This would be billet machined aluminium. Again, aluminium. Inside here is aluminium, which we'll get into in a moment, but nothing too special. Well, special enough, but in terms of Formula 1 parts, there's nothing mad about it. So we'll take off these, and we'll be able to take off the carbon fiber cover. There's a little cover on here just to stop dirt and all sorts getting into it, and probably make it a bit more. I don't know where this was exactly on the car, but I would imagine it would just cut down on any air that was passing it in terms of turbulence of airflow and that kind of thing. So we'll take off this little manifold here. It's just held on with two M4s. Again, there's no lock nuts on these, they're just tight. There was a small bit of Loctite, but not much. And it's on with the usual O-ring. So we just twist that out of there. So again, this fitting here, hopefully you can see it. Just let me have a glance. Yeah. This fitting here is nothing special. It's just an O-ring. This is titanium, swaged onto a hydraulic hose. It's got an O-ring here and a backup ring to stop the O-ring extruding out in the clearance gap. Nothing special about that. This port here, from memory, it's just a dry bearing connector. You know the way they work. They're common on a lot of things. It's like your garden hose. So you can see there the plunger goes in when you connect the hose, and it allows the fluid to flow, but nothing too special there. Even, you know, in terms of cost to manufacture, these alone are ginormous money. I think from memory, looking at the catalogue when I was speccing out other parts for my day job, these are roughly about 150 quid each, just that fitting here. So yeah, they're big money. So that should, from memory, come off, I think. Oh, let's take off these as well. So these hold on the transducer. This is a third party part, not made in house. The name won't come to at the moment, but they're a standard enough Hall effect magnetic linear transducer. So we just take off these two bolts there, and that should come off. Yeah. So that's the transducer that measures the piston position. Now, in the inner bore of this, there's a rod attached to the piston shaft that goes up in here. So that can measure then, you know, in terms of resistance on these wires here, you know, where it is. It can sense where it is inside the bore here. Now, this is held on with this bridge, which is billet machined aluminium as well, onto the top of the heat exchanger. Now you'll see here two little shims dropped out. Now these are on every part. They are on every part of this type. These parts are custom shims because, due to the manufacturing method of the heat exchanger itself, this could end up a different height. So these shims are required in order to get the transducer height back in check with the piston travel height. So that's just, they'd be custom, you know. It's just, as I said, to deal with stack up. You'll see why the manufacturing could be, you know, plus and minus a few microns with this part of the minute inside. But anyway, they're the shims. So this part should pull off, hopefully. It's been a while since I took this apart. Yeah, it's going to come off now. Let's check out these two bolts as well. And there we go. So that's just a manifold. It's a 90-degree manifold with a tap in the side. Nothing too special about that. And it attaches onto a port here. So with that all off, it would now allow me to take off the carbon fiber cover. Now this cover was bonded on with RTV, which is a room temperature vulcanization product. It cures at room temperature basically. Let's call it a silicone mastic. It's just handy for assembly. You can see it there. So that took a bit of work to cut that off and not smash the cover. So the cover, as you can see, is just carbon fiber made in a mold. Now the rough side is on the inside, so smooth side on the outside. So the mold tool would have been here. It would have been laid up inside, vacuum bag in there. That's why you have your shiny surface on the outside. Now, I've looked at a lot of carbon fiber parts over the years. This one is extremely thin. I think from measuring it from the article, it's I think 0.2 mil, 0.25 mil thick. So very, very thin, like a quarter of a millimeter. Like the thickness of a drinks can, you know. But again, it just covers up all this crack here. So this is the heat exchanger. Now I'll probably pause it after I've spoke about this just to break the video as mentioned, but let's have a look at it. So when I looked at this first, I could see that it was a load of layers, and I said, right, they've obviously, you know, machined each layer, bonded it together, machined another layer, bonded the waterway inside it, and bonded them all together, and then welded on the manifolds. But it wasn't actually that. It wasn't actually made that way at all, or even, you know, countersink bolts to hold them all together with O-rings. They were actually diffusion bonded, which is the first, I think the first Formula 1 part I've ever seen that was diffusion bonded. It's pretty cool. So I'll pull this off and we can look at it a bit closer. Now this part I've cut, it's important to note, I've cut this part, just leave that aside for a second. To properly study this part, I've actually cut it in half down the center, as you can see there, just with a very thin, a 0.5 millimeter thick slitting saw on the CNC machine. So I mounted in the vise and just parted it off to make two parts of it. Also as well, these manifolds, I've machined them away just to see the stack up inside. So this manifold here would have been covered over, you know, and again, this one here would also have been covered over, but I machined them away just to see what was going on inside. So in terms of, you know, water to oil heat exchanger, obviously the water cools the oil. You know, the oil would run it, the hydraulic oil would run it, I don't know what, I guess, let's just say 160 degrees, and the coolant may run it, I don't know, 105, 110. So there is a good bit of heat to be pulled away from the oil. And it's nice to do it this way because if you mount, obviously if you mount a separate hydraulic oil radiator in the airstream, it causes drag. So if you can somehow exchange that with the coolant, you know, you're not putting a radiator in the airstream and causing drag, which causes you know, more horsepower or pulls off your speed. So these manifolds, that's what it looked like there. This one was machined away. These were both the same. These manifolds were TIG welded on to this assembly once it was made, and then you have your standard, you know, every second one, like where you can see the open pattern here. That's where the oil would go, and on the odd one between them, either one, that's where the water path would be. So they're very close to each other, and you know, they swap temperatures. So again, this one here is what this one would look like, but machined away. You know, you can probably see the machining marks there, hopefully. Let's zoom in a bit, you may be able to see them. So you can see where it was machined, and again, if I just turn it to this side just to be clear, you can see as well where that was machined, and the radius of the cutter here. These are plugged off, obviously. I think I had them marked, but they're rubbed off now. It's still very oily and dirty. I think these were water in and coolant in, coolant out. This one was hydraulic oil, and this one was also hydraulic oil. So, you know, it had run through and flow through it. This port here is a little short, just a short fitting. I don't know, did you see it when I pulled it out there? But it goes in there, into that housing there. It's a common way to do things, you know. It just it allows a bit of tolerance stack up when you're assembling something, you know, with different temperatures. If this part was to grow, you know, a solid bar could stress fracture. I think it was done mainly for the main cylinder head feed on the DFV, if I remember correctly, or the V6 turbo Cosworth in the early days. The head was supplied with just these alone. They were, you know, about 9 inches long, or whatever, 235 mil long, and it was solely that there was no block to cylinder head oilways at all at the gasket interface. It was fed externally with these tubes. It just saves, you know, drillings or stack up or other leaks issues. I mean, these are well understood, you know, O-rings, and they're fairly simple to do and lightweight. But leaving that aside for a moment, let's break into this. So this part initially confused me a good bit. As I said, I thought it was a whole lot of discs that were machined and then bolted together somehow or held together with O-rings, but it wasn't. Now if you look at the external finish on them, confuses me even more, because they're actually a sandblasted finish, like a guillotine and sandblasted finish. I'll try and hold up the camera there so you can hopefully see the finish. It's just a weird, non-tolerance finish. So that got me thinking, and I was thinking of the many ways that it could be held together, but I had worked on a project many years ago, and it involved diffusion bonding, and the more I looked at it, I thought, it must be that. And then, as your mind goes, I thought, geez, it can't be that. But it actually was diffusion bonding. So all these parts would be made as separate, like that'll be the top cap, this will be the bottom cap, there's an intermediate ring, there might be, I don't know how many is there, let's say 25 of them. And they'd be all stacked together, and these fins then stacked as well inside them. And the process, as I said, was diffusion bonding. So the parts are all stacked between two platens. Let's say, let's do it sideways, but it would be vertical in a press. So they'd be stacked between two platens like that, and they'd be put in an oven, which would be taken to, let's say, 750 degrees, just below the melting point of the aluminium. Now it's important to note that these parts would have to be spotlessly clean on all faces. They'd have to be smoothed to about 600 or 800 grit sandpaper, wet sanded, really smooth, really cleaned with isopropyl alcohol, and not touched, because it has to be just pure aluminium touching aluminium. And they're put together, as I said, between two platens and in an argon environment. Now, as it turns out, it doesn't actually have to be done in an argon environment, but it's just a safer bet. So they're stacked, heated to, let's say, 700, 750 degrees, and there's huge pressure put on them. Now, you're talking many tons. I don't know exactly on a part like this with, whatever area it is, but let's just say, 15 tons, 20 tons, and it's left there for about 9 hours. And because it's so close to each other, each part is so close to each other, and because they're so clean, the part beside it actually becomes the other part. So it thinks, right, I'm so clean, and hey, look, I'm going to join onto that. It's part of me. So they all fuse together at an atomic layer, which is pretty cool. It's similar in ways to what happens with aerospace parts. It's called cold welding. It's a big problem in space, where there would be no air or atmosphere, and parts that are in close proximity to each other or have very close tolerance will actually weld to each other. And it's similar. It's a similar, phenomenon, if you want, but not identical. But so they're taken out then from the press, and it's all one unibody. Now, if I can clean it a small bit, I looked at this under the microscope, and I can't remember the name of the company in the UK that specialises in it, but if they're looking at this, I mean, it's a hit and miss process in ways, as in you'd have a 25% failure rate just because of cleanliness, and there's a whole other lot of things that can go wrong, but they did a super job on this. Obviously you can pressure test them afterwards, to see if there's any leaks, but you wouldn't always sense a leak between an oilway and an oilway, because it'd be the same pressure. You would sense a differential leak between an oilway and a waterway or a coolant way, because there would be a differential pressure there, but own to own there wouldn't be any differential, so it'd be harder to pick up a bleed or there, between them there. But they did a spectacular job. I looked at this very closely under microscope, under a high powered expensive unit, and I'll just bring in there, you're not going to be able to see it, but it's literally a perfect joint. There's no witness marks. It is a unibody in its form now. So yeah, that's pretty cool. Sorry, it's very dirty. There's oils coming out of it. But you know, when they're, if you keep in mind that they're all separate layers and they're just fused atomically together with pressure and temperature, it's pretty cool. So that was that part. Now the advantage you can see the swarf still coming out of there. There's still oil in it. The advantage to diffusion bonding is you can make something extremely light. You know, like these wall thicknesses here. This is about 2 millimeters on the outside, and the interlayers then are, I think, about 0.35 millimeters. So you can go extremely thin. You know, like you could make all this thing out of machine plates. You know, with like you see all the gamers now with them doing CPU coolers where it's just two machined alloy plates with a machine track for the coolant in them, and they'll bolt on another one with an O-ring. But to have a bolted interface, you need, you know, pretty strong areas for the bolts, bosses, and that kind of thing. But with this, because it's all just going to be one body together and fused at an atomic layer, it doesn't have to have any, you know, bolt areas. Or again, you know, you could weld it together too if it was very thick, but you know, you're not going to weld all those together because it'd be just crazy. But so yeah, in a nutshell, diffusion bonding, a heat exchanger like this, very lightweight. There's many ways you can design it, and you can also make it as complex as you want, you know, as long as it's all in the one plane. Now again, you could make this, you know, funnel shaped if you wanted to. You just make each layer bigger, and there'd be steps outside, and you could machine the inside any way you wanted to in each plate, but they'd all fuse together in whatever shape you want, whatever passageway is. So yeah, very cool tech. If aliens landed, you know, I'd hope to see this sort of technology on the spacecraft and not many other things that we've seen before. But I'm going to pause the video now, just so that it's easier to upload and edit, and we'll move on to the accumulator. Alright, so I'll speak to you in 1 second, guys. So hopefully that edit was fairly smooth, or as smooth as possible. So on to the accumulator itself. So this, as I mentioned, is a piston type accumulator. The whole assembly is again mentioned aluminium. It's hard anodized, as you can see there, the brown color. Obviously there's a whole lot of ports which I won't go into because I literally don't know where they go. But the main ones are this is hydraulic, and this one here would be the nitrogen fill port, which we'll get into in a moment. Now, just to recap, this part here, which I took off at the start of the video, would have gone on like that, with the two bolts. You can see them there. So there's a little fitting here. Because that's a bolted interface, they needed a tolerance, or a tolerance stack up. You know, it could be bolted here or here or here or here. So they needed some way of axial control on that interface. So they put in an axial fitting here, which is again, you know, like a 20 mil long fitting, again with an O-ring and an anti extrusion backup ring, and it'll be the same here. Now, in reality, this part, you know, from looking at a lot of Formula 1 parts, it weighs a ton. Now, I probably wouldn't have done it that way if I was designing it. The reason this has to come off is so they can put on the heat exchanger over it, like so. I probably would have broke it here if I was designing it, you know, so that this neck would screw in to the top part of the housing, and you'd still be able to clock it, you know, with this ring here where it clamps down. Just get away with this. You could machine it all as one, and it wouldn't weigh a ton. But anyway, we're not trying to redesign the part, we're just trying to look at it. So let's just delve into it. Again, this is a port for a dry brake. You can see it there. Your fitting would connect on and twist. That's just a cap there for keeping it clean in service, and there's a little thread there, so you can put in a bolt into it like so, and pull it off, so it's easy for the mechanics to sort, and the ring on it, or the safety wire on it, doesn't let it get lost. So that's that. This ring here, when I was taking it apart, I could have machined up a pin spanner on the CNC machine, you know, with various pins that would lock in here like a C spanner and open it, but I just didn't bother. What I did was I just got out a thin cut-off wheel and just zipped it, and now it cut the housing there, but I mean it doesn't matter. It just saved, you know, a half an hour designing up a pin spanner in CAD to fit into all these, trying to hold this in the vise without marking it, and then open it. You'd have to make a fixture to hold it because it was quite tight, or they are quite tight. So I just avoided all that by you know, sacrificing the housing a bit and the ring. I can live with that, and I'm sure you can too, but it's just easier, you know, and you're sure then that it will open. So it was cut, tapped open, and that's that. So this is a titanium part. It's anodized just to stop it galling with the aluminium. Aluminium and titanium and all those metals, stainless steel, like to gall. It's a huge problem, which is again getting back to cold welding. It's similar to that. When parts are so near each other, they think they are themselves, and they just stick together. So that's why that's anodized. So yeah, nice part. You know, nothing awfully fancy, but nice all the same. So we leave that over there. So this should then pull out. I marked it here with just a mark so that I could put it together correctly when I was reassembling it. There's a mark somewhere there, it's probably rubbed off. You can see the Sharpie mark there, just so that I know where it was clocked when I put it back together. So this should pull out, hopefully. Like so. So this is the main piston assembly, which moves axially. If I can just pull it out, the seals are quite hard on it, which is you can see there when I pulled it out first it was hard to pull, but now it moves easily, which is getting back to the stiction problem in the earlier mention in the video. These seals can kind of, you know, get comfortable when they're in one place for a long time and not want to move, but now it moves very easily. So, you know, it could take quite a pressure to crack this initially if it's been sitting in one place, besides a diaphragm accumulator, which would move easily. You know, the diaphragm doesn't know what's going on. So that's the one downfall with these. As well as that, the inertia of all this, you know, the piston, which is aluminium, this shaft here, it all takes quite a bit of I guess power at the end of the day to move. But anyways, that's veering off the topic a small bit. So that's the piston and plunger assembly. Now I don't know if you can see it there, just let me look on the camera for one moment. Yeah, you can do. So you can see there's a thin 4mm rod that moves up and down with that piston plunger rod, so you can just see it coming up there. So that fits inside the transducer like so, and that then records the position of the piston. So that's how that works. So let's move down again. So with this part, again, the piston is fairly straightforward to those that are up to speed with hydraulics or pneumatics. It's a standard U seal, which is what they're called because they're in the shape of a U in cross section. So the piston would be like this. You'd have a groove there, you'd have a second groove here, and in the top would live the U seal, which is this shape and that shape. which would seal against the bore wall. So that's the main oil and gas seal here. And then on the lower groove you would have a PTFE ring, which is a solid polymer ring, which would guide the piston. So the piston material here and this wall here would never actually touch. It's the guide ring here and here that guides the whole assembly up and down. So the seal is just acting strictly as a seal, and it's not got any lateral thrust on it or anything like that. And this would never touch the wall, so it never galls or makes scratches. Now the one thing that's different with this seal, which is common with a lot of Formula 1 seals I've seen, especially in the pneumatic valve train assembly, it's spring energized, which you can probably see there. Just hold it up to the camera a little bit closer. So you can see inside the U, hopefully, yeah, you can see it there perfectly. There's a stainless steel spring which is pushed down in here, like so. Now normally this spring is made from, it's laser cut or chemically etched from stainless steel, which would be probably 316. There's no need to be anything fancy. So it's pressed on there, and it just puts a little bit of pressure on this lip seal here to make it to seal. Now obviously you also have a lot of pressure coming down here from the oil, which forces this seal out even more as the pressure increases. But this just helps it when there's no pressure in the system to seal, you know. Now again, it's important to note with this assembly, the oil pressure is on the top here, from here to here, and the nitrogen pressure is on the bottom. Just should take note of the seal in orientation. That's the PTFE seal. I can just take it off there, the guide ring, should I say, which would be this one here on the bottom. Normally these are PTFE, which are impregnated with graphite, just for lubricity, and that fits in there nicely. And again, the ends are just, this one is actually shrunk because it's fairly old, but they'd normally be closer together, just they'd overlap slightly and provide a seal similar to how a piston ring would be, you know, staggered like that over each other at the end. So that's how that works. That's the seal. Quite hard. There'd be another seal obviously in here as well, put down from the top here to seal that, and it would lock into a groove. Standard O-ring here, nothing too special, and that would locate, you know, it's a chamfered here, not to destroy the seal when you're putting it in, and it would seal in on this area here. And the oil ports, just to talk about, are we finished with this part for a moment? I think we actually, on the bottom here, there's, I don't know if you can make it out on the video, you can probably see two nuts there. So there's a small nut, it's approximately 5mm, which holds in the transducer rod, and again there's another nut below that which would hold the piston on, and again there'd be an O-ring there just to seal that interface. But that's pretty much that part, I think. Yeah, that's it. Right, so the chamber itself, again, simple enough part, huge amount of material removal when they're machining it. Obviously all this would have to come out, a 5-axis part for definite. Just let me look at the machine marks for one moment. Yeah, definitely 5-axis. I know that because some of these tool marks here, which you can probably see hopefully, they follow on up to around here, which then follows on up here, which follows on down across here, which follows on to here, and again up along here. So this would all be on a moving, you know, A-axis trunnion, and it would also tilt that way in the C-axis, and obviously you have X and Y. So it was all done in one hit. Now it would probably done in two fixtures though, because they would have to machine all the external area first, or machine it nearly to net, and then do the finish bore and hone that, and then finish the outsides. Because as you know, when you're machining aluminium, if you were to machine all this to finish size and then machine the inside, the material movement from the inside would cause the part to change shape slightly where there's heavy areas, and your outside atoms then would be incorrect. So you have to take material off, you know, both sides, and then finish with your last datum finish, which will be the inside here last, just to make sure all the stresses are gone inside the part. In terms of surface finish, from feeling it, the inside is different to the outside, so I would suggest that it's probably been bored and honed, finished, anodized then, which would be hard anodized, class 3, and I would say it's probably done with the sealing coat then of PTFE, which would be fairly common, just for bored surfaces like that. It's very slippy. I remember one time a long time ago in a factory, I think it was possibly in Germany or China, I can't remember, where a surface finishing company there was a team of us, they invited us all to feel how slippy the sealing solution, the PTFE sealing solution was. And I remember that evening at dinner, I think it was 7 or 8 people were letting their glasses fall, or their cups fall, or plates, or phones, and everything like that. Just their hands were so slippy after putting their hands in the solution. But it's a very good finish. Like, you can hopefully see it on camera. It's a glass-like finish, you know. But anyways, that's the basics of that part. Again, on the bottom here, this would be where it's charged with nitrogen. Now these are blanking plates when it's removed off the car. This will be charged, there'd be a fitting on here, it'll be charged, same with the oil, you know, it'll be filled from whatever port. There's a small filter down there on the nitrogen side, which you can hopefully see. It's like a tiny little gauze filter, just there at the bottom. Now I recognize that filter because I've worked with them in the past. Has been supplied by I think it's Lee Micro Hydraulics in the UK. They do a lot of one-way valves for aerospace and for Formula 1, for medical, so that looks like that. So that will be just a last resort filter, in case, not that the gas will be dirty, but just in case that the dry brake or the fitting interface would have collected up some dirt when they're purging it with gas, so that it wouldn't get in and get behind this seal, which would destroy it. Is there anything else on this part worth mentioning? The brackets themselves, these would locate onto brackets somewhere, probably where lower down in the engine or lower down on the car, the monocoque. Just because it's a fairly high mass part, you want the centre of gravity lower. So these would just locate, clearance fit onto mounts. Now there is one integral mount here which would be similar on the car, which these dowels would locate into. Now from feeling it, it is a rubber mount. There is compliance in it. It feels like a 90 Shore or something like that. That'd be an off the shelf part. It's just pressed in and held in with like a circlip. You can see the various hydraulic ways in above the piston there, another one there, and there. So yeah, this actually is an interesting part while we're at it and finishing up the video. It just goes to show the lengths that they go to for making parts. So this here is a bung, just a bung to hold everything in place while it's not in service. But this clasp here, as you can see, this is a blanking bung, which should come out. Yeah, it's just an aluminium blanking bung to keep dirt out of that while it's not in service. Again, threaded, you can pull it out. But the lengths they go to, like with this clasp, this is a titanium part. it's just obscene machining. You know, the cost of that, it's just unbelievable. And again, this part would have to be machined. It wouldn't be machined that way, which would be fairly easy. Looking at it machined this way, which would take so much longer because of the geometry. But I'll just zoom in on it. Something else. Just hold in a bung. Huh. To have that budget, huh? Anyway, that's it. So I have another part lined up, which I'll probably do in what, like tomorrow evening or something like that. It's all lined up, ready to go, and I've kind of got into the video thing again, and I'm excited. So again, not to flog a dead horse, the reason this video exists is because of the influx of new subscribers and views. So I hate to say it, like and share, and don't even like, just if you know someone, just say, hey, look at this video, I think it's cool, you might be interested. And again, in the link up there, the little coffee cup, buy me a coffee, it'll support the channel for buying these parts. And on that buy me a coffee link, there's a commissions section. Just have a glance in there. If you know someone that's into Formula 1 parts or like their tech, you might see something there that like could be a handy present. As I said, this is for sale. There's a load of other parts in there. Have a look. You know, it's not going to do any harm. And if you don't do any of that, at least enjoy the videos. Alright lads, have a good one, take care, good night.